Figures 8.15 and 8.16 of your textbook present the idealized model of atmospheric circulation. We're going to develop that model today. 2 rules of thumb. We know warm air rises, moist air rises, because warm, moist air is less dense. And so as it rises, just as a weight lifted off of your shoulders relieves pressure, so too will hot air rising create low atmospheric pressure. Cold, dry air, on the other hand, will sink. And when it sinks, it presses down to create a zone of high pressure. Let's see how this works within the Earth system at different latitudes. Where do we have our hottest, wettest air? That's right, where solar energy is most concentrated, at the equator. So here, at the equator, we will draw an arrow moving away from Earth's surface. This arrow represents hot, moist air rising into the troposphere. Now, as it rises, the moisture in that air will condense into clouds, and it will rain out in a narrow band close to the equator. That is in the Intertropical Convergence zone that you read about this week. And as it loses its moisture and as it expands in the upper atmosphere, it's going to begin to cool. And so that cool, now dry air will descend at 30 degrees latitude, both north and south. Now, if we add an arrow here to connect head to tail, not head to head, oh, that's wrong, but head to tail, then we have just drawn 2 convection cells. We call these convection cells the Hadley cells, so named because of the gentleman who first described them. And they are counter-rotating convection cells in the atmosphere. Now we know convection is driven by a central heat source. We saw the same process happening in the mantle. In this case, the central heat source is heat from the sun being deposited in the equatorial zone and re-radiated to the atmosphere. Now we also get relatively warm, moist air rising at 60 degrees latitude. You will understand why that is the case when you jump into Chapter 9 and learn about western boundary currents and transverse currents. But as this warm, moist air rises, just as it did at the equator, the moisture is going to condense out, and cold, dry air is going to sink around 30 degrees, and also up at the poles. Now, where this cold, dry air sinks, this is where we're going to have high pressure. So here at the poles, we have high pressure air, and here at 30 degrees, we have high pressure. This is cold, dry air creates a very arid climate at those latitudes. So you will often find across the world the distribution of deserts is explained by this model. Where cold, dry air descends, that's where we have our most arid climate. Also, incidentally, where we have our saltiest sea surface salinities. Now, we have not quite completed all 3 convection cells in each hemisphere. We've got to add arrows connecting head to tail. And when we add these arrows, we have completed the 6 convection cells, 3 in each hemisphere. From 30 to 60 degrees, we call this the ferrule cell. And from 60 to 90 degrees, we call this the polar cell. Now, there's another important rule of thumb that you may have realized here. That is, the direction of air motion is controlled by air pressure. So we've labeled our high pressure zones, but we have not yet labeled our low pressure zones. That is going to be all of the places where air rises at the equator and at 60 degrees north and 60 degrees south. Now, air is always going to move from zones of high pressure to low pressure. And so we can see these black arrows, in fact, represent the direction that surface winds blow over the surface of the Earth. These give us our prevailing wind direction. But they're going to be modified by Coriolis effect, which says in the northern hemisphere, motion will be deflected to the right, and in the southern hemisphere, motion will be deflected to the left. So if we pretend we are the wind in the northern hemisphere Hadley cell, and we veer off to the right, it's going to look like I'm drawing this arrow to the left, but I want you to pretend to be the wind. And if you are headed south and you turn right, you are going to be going west. Go ahead and pause the video and convince yourself of this if you need to. In the southern hemisphere, Coriolis effect causes deflection to the left. So this north-moving mass of air is going to veer to the left. These arrows moving generally to the west are the trade winds, the easterly trade winds. We call them easterlies because they start in the east and move to the west. Now we can do the same thing between 30 degrees and 60 degrees north. This air is moving polewards and it's going to veer to the right because of Coriolis effect, producing the prevailing winds that we experience here in Los Angeles, the westerlies. In the southern hemisphere, this is mirrored, but now we're moving to the south. We turn to the left, and so turning to the left takes us to the east if we're going south. These are the southern hemisphere westerlies. Last but not least, in the polar cell, we have air moving back towards the equator, and the northern hemisphere, it's going to veer to the right, and we get a pattern of arrows that looks just like our trade winds, but we call these the polar easterlies. And this pattern will be mirrored in the southern hemisphere, where Coriolis effect deflects motion to the left. So this is the idealized model of atmospheric circulation. A couple of things I want to point out here. At the equator, where the trade winds come together, they are converging. We call this the Intertropical Convergence Zone. You will read about this in your book. I abbreviated ITCZ, Intertropical Convergence Zone. This represents the meteorological equator that divides the world into equal energy hemispheres. It's an imaginary line, of course, but a lot of important weather and climate processes happen across the ITCZ and indeed helps to explain how ocean surface currents move. Now there's another place on this model where winds converge, and that is at 60 degrees. Here, the polar easterlies collide with the westerlies, but they're moving in opposite directions. The easterlies going to the west and the westerlies going to the east. This creates the potential for a lot of frontal storm systems. And so we call this latitude the polar front. And you will read about the polar front and its influence on storm systems. So there's just one other place to label here, 30 degrees. We call these the horse latitudes. It's rather morbid how they got their name. But it has to do with the fact that where air is sinking and likewise where it's rising, we don't get surface winds. The air is either moving up or it's moving down. It's not really blowing across the surface. So I hope this was a helpful exercise to clarify figures 8.15 and 8.16. Of course, if you have questions, I know you will ask, and we will get those questions answered. So I will see you on the discussion boards, and have fun floating through the atmosphere and swimming through the sea.